to give Hamiltonian a meaning. So instead of that minus sign, it would mean like negative of energy. So we wanted it to be positive. So we intentionally added a minus sign inside of the definition. So here, right, like C equals to negative H, that's how we defined, right?
Yes.
Yeah.
Okay. Another question was for the last section that when we saw in Noether's theorem that for the symmetry case we will get conserved quantity, and so in Lagrangian we get linear momentum will be conserved. Is there any other quantity that will be conserved?
Yes, like if you find a symmetry for any coordinate that you transform, and you find that okay, something is not changing, then you have found a conserved quantity. This is how it works. So you may not know, there could be infinitely many quantity that are conserved. So let me give you an example. So you have a moment, like you have a Lagrangian for a freely moving object like L equals to half m x dot squared. Then you know for sure that momentum is conserved, that is mx dot. So p prime half of mx dot, that is also conserved. P double prime, that is let's say defined as 1/3 mx dot, that is also conserved, right?
Okay.
So technically speaking, there are infinitely many quantities, but question is, are they independent? Here in my example, no, they are not. They are one of they are multiple of one another. So no, they are not.
Okay, thank you.
Okay, is there any other question? Anyone?
No.
So to do Hamiltonian mechanics, all we need to start with Lagrangian again. So let's do the simple harmonic oscillator. This thing. So what was the Lagrangian for simple harmonic oscillator?
It is 1 mx dot square.
Half mx dot square.
Minus 1/2 kx square.
Minus half kx squared. Out of that, we need to construct our Hamiltonian. By definition, Hamiltonian is pi, that means here just p, x dot minus L, where p is defined as delta L by delta x dot. If you take the derivative, you see that p equals to mx dot. That means our x dot would be p over m, right?
Yeah.
So you need to substitute over there. So you get 1 over m p squared minus half m p over m whole squared plus half kx squared. I just substituted all x dots. Then do the algebra. You get 1 over twice m p squared plus half kx squared. That's our Hamiltonian.
Yes.
Okay. So what's the Hamilton's equation of motion for we just derived for this case? So one is the definition of momenta, that is delta H by delta P equals to x dot. That's one equation, right? So what is delta P over delta H over delta P?
This is P by M.
This is just P by M. So P by M equals to x dot. So this is basically this equation got reproduced, nothing else. So the actual equation of motion is the second one. So delta H over delta Q equals to negative P dot, or you could write P dot equals to, let's write negative over there. Yeah. Okay, so it implies that what is negative delta H by delta Q, or Q means here X actually.
Minus kx, just.
This is minus kx. Minus kx equals to p dot. So these are the two Hamilton's equation for harmonic oscillator. So you could go in two ways. You could try to actually integrate these two equations and find the equation of motion, like to find the solution to the equation of motion, or you could find the usual equation of motion by substitution. So if you substitute that p over there here, so you get negative kx equals to p dot, means p is mx dot, so ddt of mx dot, which is basically mx double dot plus kx equals to 0. So this is what we got from Newton's law, right? So by substitution you get that. But when you want to integrate this thing, you do not substitute. What you do is, in many cases it works, it won't work. So here you have two equations, that is dp over dx equals to negative kx, that is one equation, and another is dx over dt equals to p over m. You just do this thing by chain rule. Oops, I made a mistake here.
And dp over dt.
Yeah. So by chain rule, dp over dx is nothing but dp over dt into dt over dx, right?
Yes.
Which is nothing but dp over dt divided by dx over dt.
Yes.
So you just take ratio of those. So what is p dot or dp over dt?
Minus kx.
This is minus kx divided by what is dx over dt?
P by m.
P by m. So now you have a first order differential equation in terms of two variable, like here x is the independent variable and p is the dependent variable, so you can integrate it. Actually you're not doing any second order differential equation anymore here, so it's integrable, right? So what you can do, you can actually take this thing on the other side. So p by m dp over dx equals to minus kx. So take dx on the other side, so you get p by m dp minus kx dx, right? And you can integrate it with appropriate initial data, so it gives you this. So half p square by m equals to minus half kx squared.
It is actually basically the energy conservation.
Yes, this is the energy conservation equation. Yeah, this is the first order, like usual in many cases, that energy.
But we could easily say that Hamiltonian is time independent, and so
yeah, we
it
could
should
do
be
that.
constant.
We could do that, but instead of doing that, like I wanted to do a formal integration procedure to show this.
Yeah. Yeah.
Okay, so now you need to substitute the initial data. Say at initial time, like when t equals to 0, your x equals to x naught and p equals to 0, like you stretch it to some point and release, that kind of situation. Then what would be your c?
Then c would be, well, here x dot equal to 0, right?
At t equals to 0, p equals to 0, right?
Yeah.
So you have half k x naught
Yes,
square equals to c.
Yeah.
Now you substitute that thing and you get half p square by m equals to negative half kx square plus half k x naught square. You could simplify this to be half k x naught square minus x square, like that. This is basically your conservation of energy equation. Now you need to do another integration, right? Because it's just first order integration you performed. You need to perform another integration to get the motion actually.
Yes.
So what you do at this step, you actually substitute your P. So to take everything on the other side, so this half cancel out. Take M on the other side, it gives you MK, and take square root, it gives you MK multiplied by x naught square minus x square. So this is your P. But for P, we know this is basically what is our P? It is mx dot from the first Hamilton's equation, right?
Yes.
So now you divide both side by m. So you get x dot equals to the square root of k over m into x naught square minus x square. So dx over dt equals to this thing. Dx over dt equals to that thing, right? So you can actually take dt on one side and take this whole thing on the other side. So dx divided by square root of k over m x naught square minus x squared. Oops.
Sine.
Yes, it'll give you sine something. So integration of that thing plus some c.
Sine inverse, sine inverse.
So you get let's call it instead of c, call this initial thing to be delta. So it gives you t minus delta equals to what's the integration of this thing?
Something into sine inverse x.
You need to be precise, like.
Well, actually, we can
So
root over k by m. We can just take it outside of the integration.
yeah.
Root
So
over k by
1
m,
over square root of
which is
k over
basically
m.
omega.
Yes, basically omega. So yeah,
And then
you have square root of x naught square minus x square.
Yeah.
So now divide the whole thing by x naught. So take x naught out of the integration, right? That's the procedure. So it gives you 1 over x naught here, 1, right?
Yeah. Yes.
And then you have 1 minus x by x naught whole squared.
Yes.
So this x naught can be combined over here to give like d of x by x naught.
Yes.
So you have square root k by m multiplied by t minus delta equals to sine inverse x by x naught, right?
Yeah.
So you got your solution to the equation of motion is x equals to x naught sine of square root k by m into t minus delta. Now you substitute your initial data and find what your delta is, and you're done actually. So actually I can actually write your delta. We can actually solve for delta as well, right? We know that initially your x equals to x naught. We know that at initial time, like at t equals to 0, x equals to x naught. So that gives your delta to be pi by 2. You need to see why.
Root over k by
No, root over k by m doesn't matter even.
Where's the question?
So let's substitute the initial situation. When t equals to 0, you get x equals to x naught negative, because you had here a negative sign of square root k by m into delta. Oh, actually square root k by m into delta would be pi by 2, right?
Yeah.
Okay, yeah, I see it. So at initial data, like x equals to x naught, so x naught is this. So you have sine of square root k by m into delta equals to -1. So what is sine inverse of -1?
Minus pi.
Sine inverse of -1.
Minus pi by 2.
This is minus pi by 2. So
Yeah,
now we
yeah.
can substitute over here and we get final solution to be x equals to x naught sine of square root k by m into t and then plus pi by 2, right? This is the solution. So as you can see, like Hamiltonian motion, equation of motion, they actually help us integrating the system, not just producing differential equation. That's the important part. We can actually do like a complete integral of pendulum system as well, that we never saw in elementary mechanics. We can do that as well. So yeah, if you have a question, proceed, then we'll do the pendulum problem, and for now it will be enough today. Enough for today. Hello.
Yes, well, we can hear you, but I think you don't have.
So do you have any question? Anyone? Am I going too fast?
No.
Okay. I think you guys can follow, right?
Yes.
Yes.
Okay. So should we proceed to pendulum problem as well?
Yeah, I think.
Okay. So what was our Lagrangian in pendulum system? Like this?
In the Cartesian coordinate system.
No, in
Oh.
polar, final polar version. What was that?
Well, I didn't write that. Half m r square phi dot square.
L square phi dot square, where L is the length. Then
Yeah. Then
plus, I believe, m mgl cosine
Cos phi, yeah.
cos phi. Is
cos
it
phi.
correct?
Yeah, cos phi or sin phi, whatever.
Is it cos or sine? No, it doesn't.
Yeah, cos phi.
It's cos phi. Okay, okay. Okay, great. So what would be the Hamiltonian for this case? So to find Hamiltonian, first we need to find the momentum, corresponding momentum, like P phi. What is P phi? P phi is delta L by delta phi, right? Delta phi dot. Delta L by delta phi dot. That is ml square phi dot. Right? It implies
Yeah.
phi dot equals to P phi divided by ml square.
Yeah.
So now Hamiltonian is P phi dot minus the Lagrangian, that is half ml square phi dot square minus mgl cosine phi. So now substitute phi dot. So if you substitute phi dot, you'll get P phi multiplied by P phi by ml square minus half ml square, then phi dot square would be P phi square divided by m square L to the power 4, right? Minus mgl cosine phi.
Yes.
So now it simplifies. You those m cancel out, like one of those m cancel out, two of those L cancel out. So we have finally 1 over twice m L squared, and on the top we have P phi squared. And then finally we have minus mgl cosine phi. This is our Hamiltonian, right?
Yeah.
Okay, so now what's the equation of motion? So one of the equation of motion, that is basically the definition of momentum, is delta h by delta p phi is what?
This is p phi by ml square.
This is phi dot by Hamilton's equation of motion.
Oh, okay. Sorry. Yeah.
This implies, if you take derivative, that implies p phi divided by ml square equals to phi dot, and that is consistent as well, right? And that should be. And then negative delta h by delta phi, it has to be equal to p phi dot, which implies, what is this derivative? So the only cosine phi explicitly we have here. So this negative and that negative becomes positive, but taking derivative you get another negative, so that is negative mgl sine phi, right?
Yes.
That equals to p phi dot.
Yes.
So one way you could do, like you could substitute the above equation. You substitute this thing inside of here. What you get? P phi, from here you get like p phi equals to m l square phi dot, and taking dot you have p phi dot equals to m l square, that's constant thing, then phi double dot. And from this side you have minus mgl sine phi. So some of the stuff cancel out and you get phi double dot plus g by l sine phi equals to 0. This is one way you could produce the previous equation of motion that you already know, right?
Yes.
But to integrate, what do you do? What you should do to integrate this system? Because we know we do not know how to solve this
the previous system. P dot
previous
is equal
procedure,
to
yes, take fraction.
dp by d phi into phi dot, and phi dot is
Yes.
there is equation of phi dot.
P phi dot, yeah, we just remember what we did last time. So p phi dot over phi dot is nothing but dp phi over d phi, right?
Yes.
Yeah.
So equals to now substitute. So on one side you have like on the top you have mgl sine phi, and on the bottom you have what? P phi divided by ml squared, right?
Yes.
So now you're
This is-
ready. Did I make a mistake?
This is mgl sine phi. There should be plus and anything.
Why?
Okay.
Why there should be a plus?
Oh no. I mean,
Three name minus. Why? We had 3 minus sign, so 1 minus came from
yeah,
here.
I made a mistake. You are right.
Okay, so now we do the same thing. 1 over ml squared and p phi dp phi equals to minus mgl minus mgl sine phi d phi, right?
Yes.
Yeah.
So integrating, we get 1 over twice m l squared p phi squared, right? On one side, and on the other side you get, if you integrate sine phi, you get a negative cosine phi, right? So it gives you mgl cosine phi plus integral constant. Right?
Yeah.
Yes.
So now you need to substitute your initial data. Say we have a simpler initial data, that is initially it was at rest. That means we actually took our pendulum to some point with an angle like phi naught and then released. So initially it didn't have any momentum, but initially it had a coordinate. That coordinate is phi naught, initial coordinate. So substituting that, so t equals to 0 gives us phi equals to phi naught, but p phi equals to 0. So that gives us 0 equals to mgl cosine phi naught plus p. So c equals to negative mgl cosine phi naught. Okay.
Yes.
So we can substitute it back and get 1 over twice ml squared p phi squared equals to, let's factor out mgl, negative mgl. We have no, take mgl only, cosine phi minus cosine phi naught.
Yeah.
Now we are almost done. We can actually substitute what p phi. So we actually take square root and blah blah blah. So let's do it actually. So multiply this thing by 2 and then multiply by m and l square. So we get p phi squared equals to m square g l cubed, right?
Yes.
So p phi
Where
will
is?
be oh,
There is a tutor.
now it's fine.
Yes.
Like that. And also you can substitute, instead of p phi you could substitute the definition of p phi itself. Like what was that? M l square phi dot, right?
Yeah.
So if you divide, so those m cancel out and you're left with g by l on the other side, right? So phi dot equals to square root of 2g by l cosine phi minus cosine phi naught.
Yeah.
Okay. So far we did not make any mistake, right? Like
Yes.
everything cancel out. And also like you could consider a small angle approximation here and you'll see that this is basically correct. Okay. So now final state d phi over dt equals to this thing. Like I could write it here, d phi over dt. So dt equals to d phi divided by this whole thing, 2g by l cosine phi minus cosine phi naught. And then if you integrate this thing, you have an integral constant c. Okay.
Yes.
So integration. So we are integrating over time. So t plus c, t minus c equals to integration d phi square root this 2g by l cosine phi minus cosine phi naught.
Yes.
Okay. finally what we do is we take square root g by L outside of that, and we have square root g by L over here, and then t minus, we call it the square root g by L into c is as delta. This thing equals to integration d phi to cosine phi minus cosine phi naught, this thing. Now you have to perform this integration, right? So what's the result of this integration?
It's very tough, I think.
Tell me, what's the result of this?
Elliptic integral, I think.
Yes, this is called the Jacobi's elliptic integral.
Yeah, Jacobi elliptic.
So it is defined as j of phi phi naught. So this is Jacobi's elliptic integral. It has a fancy name. So inverting this, we get this thing. Invert of whatever. This is the solution. So we got a complete solution to pendulum problem for an arbitrary initial angle. See, we do not impose any constraint that phi naught has to be small. So that's the advantage. So even for this differential equation, for the second order differential equation, we did not know what to do. Here we actually found a way to integrate that. That's a big achievement here.
Shouldn't the J
So
inverse
Hamiltonian mechanics, it actually doesn't help.
shouldn't the J inverse be a function of phi naught?
Sorry.
The J inverse.
Yes, that should be a function.
Yeah.
Yes, that should be a function of phi naught as well. So point is, in terms of producing the differential equation of motion, the Hamiltonian procedure doesn't help that much. Lagrangian and Hamiltonian almost are equivalent. Actually, Hamiltonian is worse, because to find Hamilton's equation of motions, differential equation of motion, you need to find your Lagrangian. So what's the point? But Hamiltonian helps you to integrate the system. That's the advantage.
Yeah.
Also, there is another advantage. So say you have your Lagrangian to be this. The previous example, as I did, half m r dot square plus r square phi dot square, like that. So you cannot substitute your phi dot to be a constant, because it's not a constant thing. But you know that L is not a function of phi itself. So delta L over delta phi dot has to be a constant. That is nothing but p phi, and which is m r square phi dot, right? So the Hamiltonian, from here you can write your Hamiltonian, like do the standard procedure. So your Hamiltonian would be like PR, where PR is defined as delta L over delta R dot equals to PR, which is basically MR dot. So PR R dot plus P phi dot minus L would lead you to this almost similar thing, but like this: 1 over twice m. On the above we'll have PR square. Just do the algebra, I'll find this. Plus 1 over twice m r square, but above you'll have p phi square. So now, as you have your, this is your Hamiltonian, and your Hamiltonian is, or Lagrangian was independent of phi, you can substitute your p phi to be a constant. So you can like just substitute this to be a constant. So PR square divided by twice m plus, let's say this is L. Yeah, this is L, angular momentum L. So L square divided by twice mr square. So see, your Hamiltonian is now just a one-dimensional Hamiltonian. You do not need to worry about phi anymore. You got rid of it totally. So that's another example. So actually you did an integration, but that integration is actually trivial. So this p phi equals to L, that's an integration, but that's a trivial integration. Okay.
Yes.
Okay, so I don't think I can introduce Hamilton-Jacobi today. I have to wait for next one. So I'm not sure what I can proceed to today. I have 13 more minutes, so we could utilize it. If I start it today, I cannot finish. So and it will take some time. At least 1.5 hours it will take.
We can do
Okay,
in
we
the
can talk
next
about
class.
phase space.
Okay.
No. We can talk about phase space and other spaces like integral constants. That's an important issue that we need to talk about. Constants of integration. So if you have n number of independent coordinates, n degrees of freedom, GOF equals to n, then like your QI equals to Q1, Q2 up to Qn, right? Question is how many integral constants you need to provide to solve a equation or like solve a differential equation of motion that you have this
N.
Okay, answer is no. You need to provide twice n. So for initial data for coordinate Qi at t equals to 0, also the corresponding velocity at t equals to 0.
Yeah.
Qi dot at t equals to 0. So because
Q
it's a
dot.
second,
Okay.
it's a second order differential equation, right? If you do Newton's law with n degrees of freedom, you need to provide these two data, right? So let me give you an example. We'll do this example later, so we'll study it extensively. That's why it's better to use this at this point. So consider you're talking about a system that two planets or two spherical objects that are attracting each other gravitationally and orbiting or doing something. So question is, how many degrees of freedom do you have?
One degrees of freedom.
What?
The separation between them, or well, we are observing them from a different reference frame.
No. Tell me in general, how many degrees of freedom do they have?
6.
It's a 6 degree of freedom.
6,
Why?
yeah.
So you could set a reference frame in 3-dimensional coordinate. So your 3-dimensional vector, you need one vector for this one and another vector for this one. And it's a 3-dimensional vector. It has 3 components. So 3 for this, 3 for this. So you have total 6 degrees of freedom here, right?
Yeah. Yeah.
So whatever you do, you have 6 degrees of freedom and you cannot do anything about it. Remember,
yeah,
you have to deal with 6 degrees of freedom.
Well, but there is no external.
So for this system, Huh?
Actually, there is no external force.
There isn't an external. Yeah, so what? You are still dealing
then the
with
center of mass.
6 degrees of freedom. So do
Okay.
yes, that's how, what you get from integration. You integrate and you find that okay, the integration of center of mass is trivial. So that's one thing, but that doesn't reduce your degrees of freedom.
Okay.
So
Yeah.
your degrees of freedom is 6. How many constant of integration do you have? How many constant?
1.
12.
You should have 12. You should have 12 integral constants. Okay. So what are those 12s? So in one word, you could say initial position and momentum of one particle. So that is initial position means 3 coordinate and initial momentum means another 3 constants. And here for same thing for another one. So 3 numbers for your initial coordinate, 3 numbers for your initial momentum or initial velocity, whatever you say. So in whatever procedure you follow, you have to deal with this 6 degrees of freedom and this 12 constant of integration. So by complete integration, there will be a word complete integration frequently in our language. Complete integration means a solution that includes that 12 constant of integration in this context, like twice n constant of integration, where n is the degrees of freedom. So here, usually what we do, we split this problem in a clever way. So instead of dealing each of the objects separately, what we do, we have like these are the 2 objects. So we set up a coordinate and it has a center of mass. That center of mass has a position. So that's 3 degrees of freedom here. And with respect to one of those, because another is just multiple of that, the ratio of that. So we'll see that later. So center of mass, it has 3 degrees of freedom, and one of the object with respect to the center of mass has 3 more degrees of freedom. So when you integrate the center of mass, you should have already COI for center of mass, you should have 6 constants. So 3 constant for initial position of center of mass and 3 constant for initial momentum of center of mass.
Yes.
And then with respect to center of mass, you have to deal with 6 more constant of integration or 6 more degrees of freedom.
Yeah.
But whatever procedure you follow, you have to deal with these 12 degrees of freedom in total. So what are those other 6 constant of integration? So position of it.
Yeah, the position of the first star and its velocity.
Position of say first object. COI of first object, that will give you 6, right? So
yeah.
The second one should be dependent on
By
this
constraint.
So so 3 will come from its position and another 3 will come from its momentum. So usually we do polar coordinate for, like we do Cartesian coordinate for center of mass, we do polar coordinate for the rest 3. So that's why for these 6 degrees of freedom we'll have like R naught, like 6 degrees of freedom will have like PR naught, PR at t equals to 0, then P phi at t equals to 0, P theta at t equals to 0, actually not phi. P theta at t equals to 0 because we're doing spherically polar coordinate, and then P phi at 0. Then also R at 0, theta at 0 and phi at 0, like that. And for center of mass, we will write it as like big P of x, x coordinate of this thing to be at time 0, this at time 0, and this at time 0. And then this at 0, this at 0, and this at 0. So this 12 constant we have to we need to show in our solution finally. If your solution doesn't include those 12 constants, then your solution is not complete. You're missing something.
So any reason behind considering the polar coordinates and not the Cartesian coordinates?
Yes, because it has a polar symmetry. So its potential is polar symmetric. We'll see next day. Its potential is like dependent on distance only. So that's why. So like we'll do this problem in all 4 ways, like Newtonian, Lagrangian, Hamiltonian, and Hamilton-Jacobi. So for each of this procedure, we'll look for these 12 constants. Remember. Okay, so I think I have utilized these extra minutes so far. Okay, do you have any questions?
I think some exercise problems should be appreciated.
Now, we already did 2 actually. Harmonious.
You can give us some exercise problems for.
Like go to the Facebook library I suggested. There you'll find the PDF copy of Taylor's classical mechanics, and you'll find plenty of good problems to do.
Okay.
So we have learned already so far 3 kind of mechanical system, like 3 kind of procedure to solve a mechanical system. We'll learn 1 more, and then we'll do 2-body central force problem explicitly.
Will you discuss the Noether theorem a bit more, some advanced in the next class?
No, not really.
Okay.
So if you have any question, you can ask. So okay, we'll draw some connection with like Hamilton-Jacobi procedure and Noether's theorem.
Okay.
So for 2-body central force problem, it has like 12 degrees of freedom. Like so constant, there will be constant of like 12 constant of integrations, constants of integration. So those are actually conserved quantities like imposed by Noether's theorem as well.
I have a question, a simple one, like to study the motion of the particle in the space, like whatever it is, it's a planet or anything, we use these Lagrangian or Hamiltonian equations only?
Yeah, no. We can use Hamiltonian, Hamilton-Jacobi, or Newton's law, whatever you want.
Or we can use any, okay.
Yes, it doesn't matter what you use. So they have kind of different kind of advantages from one to each other. Like for Newton's law is easy to understand and easy to apply.
Yes.
But sometimes, like if you have constraint system, then Newton's law may not be that useful because you may not recognize your force on in the first place. So that's a problem. So for planetary system, you can actually always say that what your force is. So that's not a problem. For Lagrangian, when you have like the constraint system, then it's easy to, instead of finding the force, you actually finding the Lagrangian is easier. So that's how it helps. But if you want to integrate this equation of motion, then other two like Hamiltonian dynamics and Hamilton-Jacobi equation of motion, like Hamilton-Jacobi formalism, they help.
Okay. Actually, I saw on the net there is Lagrangian planetary equation. So I thought maybe for planets, for studying planets and all the stuff we use, it's not that. Okay.
Actually, we use all of we use four ways. Four ways we learn to study two-body central force.
Okay.
Because I feel it's the best way to understand the difference between those four formalism and understand the advantages of those, like difference and advantages, and like caveats of each other, each of the problems, each of the ways.
Okay. Thank you.
Yeah. Are there any questions so far? Any more questions? Carl, do you have any question?
Not yet. I'll have a lot of questions when I dig into it a little more, I think.
Okay, yeah. But start digging in, otherwise it might get complicated.
It is complicated.
Yeah. If there are no more questions, then I can like adjourn today's class.
Thank you.
Yeah.
Thank you.
To you guys.
Thank
Yeah,
you.
thank you.